if all glaciers melted at the same time, we would see the sea level rise 70 meters. This would be enough to flood every coastal city on the planet. We would see cities such as Lisbon, New York, or Venice disappear. Although reality is not that catastrophic, at least yet, there are still reasons for concern. Studies show that the ice melting skyrocketed in the last decades, especially because of climate change and global warming. It is estimated that the average annual loss in the 90s was around 760 billion tons of ice. Now, this value is at 1.2 trillion tons per year. Greenland and the Antarctic, which store two-thirds of all fresh water on Earth, are melting at an average rate of 420 billion tons a year together. Is the catastrophic scenario mentioned earlier closer to us than we think? How are scientists working to figure this out and try to stop it? Hello and welcome to another episode of Crosstalks. My name is Adriana Costa and I will be your host. This podcast series by the UT Austin Portugal Program will walk you through the wonders of science-business collaboration. We will be exploring emerging topics in advanced computing, medical physics, nanotechnologies, space-Earth interactions, and technology innovation and entrepreneurship as we delve into the program's industry-driven research projects. Satellites are no unknown object around here, and if you go a few episodes back on the episode about my Gal Constellation project, we already found out how versatile they can be. They are especially important for monitoring climate change and sea level changes. The NASA's GRACE missions and the European Space Agency's GOES missions are monitoring sea level through the Earth's gravity field. In general, the mission satellites evaluate the local pull of gravity as water shifts around Earth due to weather, seasons, and climate. But they are not the only ones. Researchers from the UT Austin Portugal Program Strategic Research Project uPGRADE are developing a prototype to estimate how water is moving on the Earth's near surface through gravity acceleration. In the future, this could enable researchers to do similar experiments of previous missions, but at a fraction of the cost. How? Through the development of a miniaturized space accelerometer. Still not sure how all of this connects? Then let me introduce you to today's guests, Tiago Hormigo, Head of Space Business Development at Spin.Works S.A, and Chaoyang Zhang, researcher at the University of Texas at Austin. They will tell us everything about the uPGRADE project. So Tiago and Chaoyang, welcome to Crosstalks, and thank you for accepting the invitation to join me today, and I hope you're doing well.
Thank you very much for the invitation.
Thank you for having me.
So let's start. I want to ask Tiago a question. So your project uPGRADE aims at estimating how the water moves in the Earth's near surface at a regional scale. I had the opportunity to tell our audience about this. But before asking how you will do it, I'd like to ask, why have you decided to search for gravity field variations on our planet? So why does gravity matter in your context of the uPGRADE project?
So most of the techniques that are used to measure how the water moves around the planet are essentially direct observation techniques. And these involve some degree of extrapolation when estimating how significant bodies of water move around. Because a proportion of the water cannot be identified or quantified directly, because the things such as there's a lot of water underground that cannot be directly observed. There is water even on the ground that cannot be directly observed because there is things like vegetation or other means. There is underlying topography below the glaciers that sometimes we don't know about. So it becomes really difficult to quantify how much water is where. By using gravity, we can go around this problem because we measure how the entire mass is moving around. We can indirectly measure how much the gravity field is affected by the changes in the amount of water that is present. And this is a highly complementary means of doing the quantification of water to these other methods.
That's very interesting because when we think about water, I only think about oceans, but there is actually a lot of other places where we need to find water. So that's interesting. I would like to ask if Chaoyang wants to add anything.
Yeah, so should have started like in the introduction, you will mention that we are focused on the change of the gravity, right? But not the unchanged part. Because we all know the rough gravity acceleration is around the 9.8 meter per second square. But here we see the change of the gravity, right? We're actually talking about the number 1 billion times smaller than 9.8. Or you can think of like a number around like tens or 100 meter, sorry, tens or 100 nanometer per second square. That's really something very small. So like from the engineering point of view, it's quite challenging. So think about, can you, when you enjoying the, like just a kind of an analogy, when you enjoying the sun bath, like just under the sun, can you feel anything? I mean, definitely you will feel like it's very warm, but right? But other
Yeah.
than that, you cannot sense anything. But that exactly what we're gonna to measure from the upgrade. So just those tiny particles, they will just shoot on the spacecraft, and that's the kind of small thing we're gonna measure from the upgrade. And from the scientific point of view, the change of the gravity, or sometimes we also, I mean, like use a scientific term, we call that temporal gravity because it's the change over time. And then it can tell a lot about our planet. So in a short time period, the change of the gravity basically just reflect, like Tiago mentioned, the transportation or migration of the water, right? So we can just infer how the water is moving on our planet to use the gravity observation, whether it's like due to the climate change or human intervention, like just pumping groundwater from the like California, or I mean maybe it's just the natural water cycle. So like what you just mentioned, I mean in the introduction, the sea level variation, we can observe that, right? And also we can monitor the glacier melting or glacier mass loss over the polar region, groundwater depletion, like just I mentioned, over this, which is actually ongoing event in California. Or even we can use that to detect earthquake. Yeah, earthquake, right? That's just something amazing, right?
That's very
Yeah, you
interesting. I
can,
never thought you could do
yeah.
that.
Yeah, you just like you can see, we just can do a lot with gravity. I mean, the temporal gravity, not the static part. Yeah.
Thank you. So with
Mhm.
all that you have explained, so we're going to estimate how water moves in the Earth's near surface. And for that, we're going to use what you call a miniaturized space accelerometer. And first of all, what is a space accelerometer and what's special about one you're going to develop or you are developing under the project?
High precision accelerometers are typically devices that can measure tiny non-gravitational accelerations. On Earth, this type of accelerations can really only be produced either in a lab or by relatively unusual phenomena. Things like, as Chaoyang just mentioned, earthquakes, when you're measuring them from not directly above the earthquake, but from the other side of the world, for instance, or the effects of, and this is an example I've seen a long way back. When the sea is really stormy and you measure and you have a seismometer um, placed several tens of kilometers, you can still see the waves. but they're really tiny, and only these very high precision accelerometers can pick them up. So this is what these devices are for. On the Earth's surface, just to give you a measurement, um, on the Earth's surface, even the centrifugal acceleration that's produced by the Earth rotating around itself is really several orders of magnitude too large for this. It will saturate the sensor, um, even though it just cancels about 0.3% of the gravity at the equator. So in space, it's an entirely different story, because the other environmental disturbances are really much smaller. And we have learned how to model most of the physical phenomena that cause these disturbances to a very high precision, and to know exactly on which parameters they depend on. For instance, on the atmospheric density at these altitudes, on the intensity of the solar radiation, on the size of the spacecraft surface and the speed at which it is rotating about itself. So these accelerometers can be used then to extract really important information, because we know so much about the physical models that rule these disturbances in space, and we can just basically pick them apart and investigate the deeper phenomena that may be lying below. So what we can do as well from space is we can measure things over large scales, both in space and in time. And these effects, in particular with this mission, these can potentially affect our environment, as what we're trying to do is really measuring how the water is moving around the near surface. Our accelerometer in particular wants to do that. We expect to do that using MEMS, or microlateral mechanical systems, and these are small components that have been used throughout the industry in the last decades. And we're trying to have the kind of sensitivity that other types of components that need to be much larger, that can only fit in large missions. We are trying to fit this type of components in a very, very small spacecraft that's around about 30 by 20 centimeters by 10 centimeters. So really small things. So this is how it differs from most of the accelerometers, or the precision accelerometers that have been placed in space.
Okay, thank you. So basically, the idea of having it in space is that it can reduce the biases of what we can retrieve here on Earth. Am I right?
There are way too many stimuli and from so many different sources that it's really hard to tell them apart. In space, we are affected by a lot less phenomena that can really, measure substantially in these accelerometers. So we can pick apart what the sources are for these joint accelerations, and then investigate really what is below the main phenomena that we already know, that we can estimate very precisely what is going on there.
Okay, that's very interesting. So with this sensor that you're developing, you expect to have an accuracy in the order of the 20 nanometers per second square. I would like to ask Chaoyang, what does this mean? And if you can give us an example or a comparison so that we can better understand the measurement process.
So probably we should step a little back and then tell the story why, how we actually measure the gravity, right? Okay, so if you could, I mean, like just step a little bit back. So you could consider, so how we actually use the satellite. You could actually consider satellite as a scale, like the scale you use every day to weigh your weight, and then, but it's actually a scale flying over the Earth, right? For example, when you fly over Austin, it will just give you an output of the gravity acceleration of the Austin area. And then if we fly by Austin by twice, and then we subtract the first measurement with the second measurement, we know, okay, Austin gained some weight or lose some weight during maybe like a couple of days time. And then if we know there was a storm during that time, then we can calculate how many water we got from the rain over that period of time. So that's just a simple analogy, make you sense why we want that satellite orbiting the Earth, because we can measure it over a long time period of time. And now let's get to the second question of how we actually measure the gravity acceleration and why we need that very precise accelerometer. So the principle is very simple. If you can recall how we measure the gravity acceleration in the high school, we just drop a ball and we measure the time and the distance, right? And then we can calculate the gravity. But again, that's a static gravity. For the upgrade for our satellite, you can consider the satellite is the ball we dropping, but because it's free fall and then it's up high in the altitude, it's gonna just orbiting the Earth for many years instead of like we just drop it and we can measure it. But here we just got too many chance to measure its position and also the time. But here, instead of like we don't use just use a click watch or something like a ruler to measure the distance and time. Here we use the GPS. There's gonna be an onboard GPS over there to measure the time and the position of the satellite. So similar to that, if we have the position and the time, then from just again Austin, if a fly by Austin for twice, we know the position and then we can calculate the gravity. But here, there's a problem here. In addition to the gravity, we also have like, there's still some atmosphere up there. So we have the drag force, like because you're flying in the air, you got you have some force from the air. Second, you also have like just I mentioned the solar radiation. The sun is like shooting with the particles, right? And so that's why we need the accelerometer. We use the accelerometer to measure those force we don't want, and we remove those the drag force or the solar radiation from the measured gravity. And that's why we need the accelerometer or MEMS accelerometer here. And again, it's very small, right? It's like 1,000,000 times smaller than the gravity we are talking about. Yeah. I don't know if that's a sensible number for you.
Yes, it is. Thank you for the explanation. So, going a little bit back and taking something that Tiago said before, that you could do something that eventually other missions are doing, but smaller sizes. For missions such as the NASA's GRACE missions that are quite big, I like to ask if it's possible to do things that are similar to those missions, but at smaller costs, and if it's possible to maintain the accuracy, and what kind of specific research challenges those different aspects entail.
So first of all, it's important to note that because we are trying to do this for the first time or for one of the first few attempts, we will not necessarily have the kind of accuracy that the full-scale mission does have. What we're aiming at is a system that if multiplied for a few tenths, so if we instead of a single spacecraft use a constellation, we could potentially have the same sort of accuracy while having a much better time time refresh. So time every now and then we will have estimates. If we have a number that is sufficiently large, then we can get below about once a day an estimate, and that would be potentially really life-changing in a way. So what we're trying to do right now is to demonstrate that we can do the same kind of measurements that previous missions have done at a fraction of the cost. The first spacecraft typically is a lot more expensive than the following ones, and so this project amounts to about 3 million. But if we are to multiply it by a lot more, so if we have tens of spacecraft, each spacecraft can cost as little as a few hundred $1,000. So that means that we can have even a full constellation of, let's say, 100 spacecraft will still amount to about a tenth or even less than a full-scale mission. And this is what we're aiming at in the midterm.
Thank you. So basically, instead of having one big thing that measures it all, you're gonna have like a little team of satellites in a way, and all of those get data that's similar to one big satellite, right?
Right,
and with a
we
lot less
also
cost.
benefit, and we also benefit a lot from the effects of scale. So once we start building out things at in a series of tens of units, then the price per unit becomes a lot lower, and we can take advantage of that to have an overall best or better performing scientific experiment, so to speak, than by just producing a single spacecraft that will have uh, all the instruments on board fully customized.
It definitely can benefit scientific research that way, and make it more affordable.
That's the goal.
Yes. The teams, so this is a collaborative effort. So the uPGRADE project is a collaboration between UT Austin and Portugal, which is also collaborating to develop a self-stabilizing and miniaturized spacecraft with low thrust propulsion that carries a high accuracy accelerometer and insulates it from all sources of perturbation. I would like to ask Tiago, how exactly will it work?
So first of all, we wanted to use the low thrust propulsion. The intention was to enable the spacecraft to perform a longer mission, and also to demonstrate the capability that we see that will be very useful in future missions. However, it also adds some risk, and by training it off with a return and the probability of mission success, we decided to to remove it, because we knew that we could achieve the science return in any case, even without it. So this was a decision that we took. Apart from this, what we're trying to do is a system that works in a similar way or with a similar kind of subsystems that we have used previously in our own projects related to drones. And so in that respect, it's not all that different. However, the main challenge here was really to build the spacecraft to insulate it from perturbation sources. And this is an entirely different challenge. To give you a sense that of the kind of details that we have to get to, um, just the if the satellite keeps itself in a stable position relative to the Earth, it means uh, after each orbit it will rotate once about itself. Just that rotation is potentially more than enough to be measured by the accelerometers on board if they are too far from the center of gravity. So if they are more than about an inch, we will be able to measure that, even just the rotation in every 90 minutes. So that's one of the things. The other thing is, if we had solar rays that were extensible, then that will be, or deployable, that would be a problem. We would be able to measure perfectly the vibrations caused by those solar rays. And the same thing with antennas. So we had to take a lot of care in choosing which devices we could carry on board and that could be placed within the spacecraft, knowing that any device that was active would be a source of problem. Any device that was deployable was a potential source of problems. Any device that was flexible would be a potential source of problems. So there was a lot in there that contributed to the design as we have today.
Okay, and you're not only developing this spacecraft, but they're also going to develop a generic high-performance nanosatellite platform, which will be applicable to a broad set of commercial Earth observation, communications, and space exploration missions and constellations. I would like to know more about this. Can you explain to me what is this platform about, and when could it be available in the market?
Okay, so the intent for this this mission, as we see it, is that we need to remove all the risks that are introduced by just the fact that we are developing new things and trying to get them to work in space in a fully autonomous spacecraft, or almost fully autonomous spacecraft. And so we had to concentrate on that and on carrying out the science mission before we got to more ambitious stuff. Our goal here is to, so by the end of this, we will have a 6U CubeSat that can potentially perform other missions. What we have been doing in parallel to this project through several others that we are currently carrying out is we have developed a range of cameras, visual, multi, hyperspectral, thermal, etc. And we expect to use these as part of future spacecraft. So not just the platform, but also the payloads that we are currently developing will be placed in the global market, and that's, I think, one of the key motivations for us for the mission, independently of the science that we think we will be able to produce.
That's interesting. So basically, this platform would make it available for other people to collaborate.
So this platform basically will serve for a number of other purposes. Right now, the idea is that it's generic. We have also invited other entities potentially to contribute with payloads. We will do the same for future missions. And so basically right now, what we're aiming at is having a platform that works and that we can make available to others and for ourselves, of course, in the future for other purposes. We have not necessarily included already other partners in future missions. We are hoping that we will continue to collaborate with Austin, and that we will be able to do future missions with other kinds of payloads.
Thank you. I hope this is successful, that you can then involve so many other partners and to make science benefit from this, which is the ultimate goal. And now that we have talked a little bit about science and the engineering part and all that UPGRADE entails, I would like to know more about the partnership itself, which is basically a team effort. So UPGRADE is a team effort between Portugal and Austin. And I would like to first ask Chaoyang, how did each stakeholder contribute to this project? And you can start by explaining a little bit more about the Austin side and how did UPGRADE, how did it came to life?
Okay, so the Austin team, or us, we mainly focus on the scientific portion of the tasks. You know, each segment or instrument on board the satellite will affect the quality of the temporal gravity, or the change of the gravity we can get from the satellite, right? So for instance, Tiago just mentioned the MEMS, or the accelerometer. So even how we organize or arrange the MEMS will affect what we can get. So basically, because we are in a 3D space, right? We have to observe everything in the X, Y, and Z direction. So, but we cannot, because we have limited space. We cannot, just merge them into one pieces, right? We have to sort of like distribute them, and how to distribute those little piece of chip in the center of the satellite will affect the what we can eventually get. I mean, the scientific return from the mission. And so that's part of our job. So we will got some idea we got some idea from Portuguese team, like from Tiago, and then we would use our software to decide whether this one, like the A plane, is better than B plane, and what we can get from A, and then what is the error, you know, threshold for that A, and then not B. Yeah, that's sort of the thing we're working on. Also, in addition to those instruments, because we are flying in the real world, because like I just explained how we estimate the gravity, but that's a very very overly simplified scenario. So in the real world, we have, like you mentioned, we have ocean, we have ocean tide. The tide is just bouncing back from time to time, and even also we have solid earth tide. So even the ground itself is actually up and down every day, like up to decimate, although we don't sense it when we were here. But because the accuracy we are talking about, it will also be affected up to the satellite altitude. Yeah. So basically, we're just doing what we can do from our side about the science, how we got the gravity with different kind of scenario, and then what eventually we can get from the gravity, we can estimate it from the upgrade project eventually. Yeah.
Mhm. So just as a curiosity, just the gravitational pull of the moon is about 100 times the resolution of our sensor. So it's not that we can measure it because it's gravitational. So the accelerometer doesn't measure gravitational forces, but still, just to give you a sense of the sensitivity of the thing. So our team has basically discussed with the team at Austin from the very beginning, along the lines of the leadership on the science side is at Austin. Some degree of the advices that we need to develop a spacecraft that can work for this measurement principle are provided to us by the team at Austin. And on our side, at Spin.Works, we are the industrial lead, so we are building the spacecraft. And then we have contributions from INL and the University of Minho for the high precision accelerometer, and from ISQ for the qualification. So the contribution from Austin has been invaluable in the sense that there's a lot of design decisions that we would possibly not have detected or made to the spacecraft if we didn't have this close contact with them, that where we are every month or so, or even more frequently in contact with them, having meetings and showing what we have, and figuring out together how it affects what the final measurement will be like. So I think that this has provided us with a good starting point for more collaborations, and we have started to do them as well, as I think is something that we can discuss.
Very interesting to see how you can all combine your strengths between each stakeholder and make it the project come to life. And you were talking about future partnerships, and I was going to ask exactly that. So I want to ask you both if you are planning any future collaborations or next steps from this project.
Yeah. So we have already made a bid for one of the exploratory projects calls, so from UT Austin. That would be covering the ground operations because it's something that we have not focused very much in. And currently there is a bid based precisely on what we have been discussing so far. So the application of this type of satellites, such as uPGRADE, to building a constellation that is capable of performing measurements of the gravity field variations in time and space, and this is currently under evaluation. And this, so the consortium is essentially the same as on uPGRADE, and we expect to have first of all a feasibility study, and let's see where that leads us. But obviously, there we are looking to have a collaborative partnership with both UTA as well as universities in Europe, such as Delft, where we have collaboration, and other universities that are working on this gravimetry problem.
I'm very pleased to know that you are able to move on with the project after it's completed this year. That's what we strive for, is that the research and science doing that is done through these calls to progress through the years and gives a rise to another ideas and further improvements on the projects. Would you like to add anything, Chaoyang?
No, I mean, just, yeah, because I'm also part of that, like the proposal Tiago just mentioned. So yeah, I mean, but other than that, we also have a smaller, tiny proposal, right, Tiago?
Yeah.
Another one, yeah. I mean,
So,
but just basically, there's just things still going on. Yeah, like you said, that's really good news. Yeah.
mhm. So, but apart from this, I didn't mention it earlier, but we are also preparing basically a follow-up to what uPGRADE is ourselves, and there are some issues that we can will probably be able to resolve that are related to how collaborations are made between Portugal and the University of Austin. So this is something that we look forward to solving and really have them on board in the next few years to be able to complete the satellite as it is right now, and to try and build something more ambitious in the future.
That's really great. That's all the questions I have for you today. So I don't know if you want to add anything that we haven't discussed and you think is important to say.
Yeah. So I have a couple. Yeah, definitely. First, thank you, Adriel, for just inviting us to here to talk about the uPGRADE project. And then secondly, so this is my first project after my graduation from the Ohio State University. And before, I mostly just working on the scientific stuff like glacial melting and stuff like that I mentioned before. But I really appreciate this opportunity to work with our excellent Portuguese team for the uPGRADE project. I got this chance to learn how hard it is, just to realize the scientific concept from the engineering aspect. But I also learned how wonderful our Portuguese team are. They are trying to shrink the mini Cooper size satellite, like you mentioned, the Grace. That's a mini Cooper size, and to just a shoebox. That's just really amazing. And not to mention the extremely high accuracy we need to get for the accelerometer we just discussed. Yeah, I mean, all of that will be done in the Portuguese side with the leader Tiago. So yeah, I mean, everything just amazing. Yeah, just use this opportunity to to thank Tiago and the Portuguese team.
Thank you so much. We look forward to continuing our collaboration, and I think there will be other opportunities for sure. We have our eyes open, and so far things have gone really, really well between our sides, both in Portugal and in the US. So I see no reason why we shouldn't be working more often in the future.
Yep, it'll be great.
That's really awesome to hear from. Was this your first experience in a project this big, Chaoyang?
Yeah, so before, mostly like I just mentioned, although I also work on some international project, like with a bunch of other university from Europe, but mostly it's it's on the science part. We focus on how we improve the gravity and how we monitor like glacier melting, or like can we use the gravity to sense like typhoon or storm, stuff like that. But yeah, like this one, you started from the bottom, like from scratch to build a satellite. That's just like, I mean, brand new for me. And then I just learned a lot about the engineering part of how you actually build a scientific instrumental, the concept from scratch. That's really amazing for me, you know. And then that's really hard as well, like this I mentioned. Yeah.
It is definitely really good to hear that. So, with that said, we ended our conversation. And thank you again, Tiago and Chaoyang, for being with me today to explain more about your project. I wish you good luck for the rest of the project, and also good luck for your future collaborations.
Thank you very much for the invitation.
Thank you all for listening to this episode of Crosstalks. If you have enjoyed it, and even if you did not, we would love to hear from you. So make sure to subscribe and leave a review. For additional content, follow us at UT Portugal on Twitter or visit utaustinportugal.org. Did you know that we are now on Instagram? Make sure to follow our journey at utaustin_Portugal. The uPGRADE Consortium brings together scientists and business people from 5 institutions: Spin.Works S.A, International Iberian Nanotechnology Laboratory, Instituto Solidor e Qualidade, University of Minho, and University of Texas at Austin's Cockrell School of Engineering. uPGRADE is co-financed by the European Regional Development Fund through COPET 2020 and the Regional Operational Program Lisboa 2020, as part of Portugal 2020 and the Portuguese Foundation for Science and Technology, bearing the seal of UT Austin Portugal. The total eligible investment is around 2.6 million euros, with public funding amounting to 2.3 million euros. UT Austin Portugal is a partnership program in science and technology between the Portuguese Foundation for Science and Technology and the University of Texas at Austin, supported by the Ministry of Science, Technology and Higher Education in close collaboration with the Council of Rectors of Portuguese Universities.